everyone, I'm Bakhtiar and I'm going to present our work Piprima, predicting patterns in sparsity to accelerate matrix algebra. This work is done in collaboration with Donghyeon and Professor Bahar at the University of Melbourne. So first of all, introduction. What is sparsity? Well, the existence of zeros in a matrix is referred to as sparsity. Over the years, sparse matrices have become crucial in various fields, such as large language models, scientific computing, genomics, and recommendation systems. Sparse kernels are the kernels in which either of the operand is sparse. The first and the foremost kernel is the sparse matrix and dense matrix multiplication, in which one of the operand is sparse and the other one is dense. These sort of multiplications are really usual in large language models and machine learning models. The next is sparse matrix dense vector multiplication, which are more evident in scientific computing, in which we have to converge to a solution. Another example is sparse matrix multiplication, in which both of the operands are sparse. Now, how can we leverage sparsity? As you can see, we have a very big matrix on the right side of the slide, and we have very few non-zero values there. So we can do the matrix compression. And what is the advantage of doing matrix compression? It reduces the storage required to store this big matrix. When we reduce the storage requirement, we are basically speeding up the computations by mitigating the data movement overhead. The main goal of sparse matrix compression is to discard the zeros and only store the non-zero values along with the relevant metadata. There are different compression formats out there. The most commonly used is the compressed sparse row format, in which we have sparse matrix. We have offsets, which keep track of the number of non-zero values per row so far. Then we have indices, which keep track of the column indices of all the non-zero values, and then we have the values themselves. But there are some challenges using these sparse matrix compression formats and doing multiplications and computations with the sparse matrices themselves. The state-of-art sparse accelerators, for example, the first one, Extensor, proposes a hierarchical elimination of computations to avoid unnecessary data transfers. Another state-of-the-art sparse accelerator is Tensaurus, which employs a novel format for accessing sparse data to optimize memory bandwidth using tiles. However, we noted that these state-of-art accelerators do not leverage the pattern of sparsity in a sparse matrix and consequently results in fine-grained load imbalance. Next, I'm going to talk about what fine-grained load imbalance is. Here we assume that we have a stream accelerator, including a pipeline buffer. To process a sparse matrix, such as the one shown in this figure, for each row we need to first read the non-zero values in that row, and then we have to do all the computations in a pipeline fashion. Given such a pipeline, there are three cases. The first case is when we have serial placement of non-zero values across the on-chip memory blocks. As you can see, there is only limited pipeline factor that can be achieved, and there is no possibility of having a parallel factor within our computations. The next one is an imperfect distribution, which means having more than one partition on-chip memory, but an imperfect distribution of non-zero values. It will reduce the read time, and we can now parallelize and pipeline computations better. But as you can see, it is still subpar parallelism because the distribution among the on-chip memory partitions, they are not ideal. The ideal case would be to access the non-zero values distributed across the banks of on-chip memory, and by doing that, we can ensure that we are reading all those values in a pipeline fashion, in a parallel fashion, and hence we can get the maximum performance out of it. Decompression is also an overhead. We have a compressed matrix, we have to decode the metadata, and then we have to locate the non-zero values. And once we have the location of these non-zero values, only then can we continue with the relevant computations. We had two observations about sparse matrices. The first one was the structural coherence. We observed that even though sparse matrices are highly random, there still exists some sort of structural coherence in these matrices. Here in this graph, we ran experiments on SuiteSparse matrices. The goal was to find out what percentage of rows in a matrix mimic their last neighbors in terms of non-zero values. For example, if row 2 has 10 non-zero values, it is highly probable that row 1 will also have 10 non-zero values. The key observation based on our experiments was that on average 78 to 85% of the rows, they are homogeneous to their last few neighbors in terms of non-zero values. The second observation was that we can, the sparse matrices, we can categorize them in two categories. The first one is diagonal matrices and the other one is random matrices. The key observation here is that the non-zero locations in a strictly diagonal matrix, they are already known. We know what are the locations of the non-zero values in a strictly diagonal matrix. Using these two observations, next we will move to the architecture of Piprima. The key insight is that to enable finite load imbalance, Piprima predicts the non-zero values for the current flow based on the history of the previous flow. This is similar to the branch predictors in CPUs. Using such a simple predictor by just reading a single counter, Piprima distribute them evenly as values and indices are streamed. The first thing is how we are doing the predictions. We are simply using counter-based predictors to predict what is the structure of the underlying matrix or the type of the matrix. The first predictor is the DR matrix predictor. It predicts if the given matrix type or the matrix itself is strictly random or if it is strictly diagonal matrix. The next one is the energy per row predictor, which predicts how many number of non-zeros are in a specific row. The decision is made based on the non-zero values in the subsequent row. And as you can see, these two predictors they can be employed using simple state machines. For the architecture of Piprima, we have these counter-based predictors. As you can see, like any other predictive system, we have to verify if the predictions made were correct or not. The prediction inspector, they are responsible for verifying the predictions made by the counter-based predictors. If the prediction was correct, the execution will continue. If the prediction was wrong, we have to pay the price, we have to fetch the pipeline, and then set the values of the state machine to the correct output. The next is the memory components. These components are the on-chip memory components. We have the compressed data memory, responsible for storing the sparse operand, and then we have the dense data memory, responsible for storing the dense operands. Next, we have the computational unit themselves. The basic computational unit in our architecture is the if-1 unit. Dense matrices may have some zero values. The comparator in if-1 unit checks if that is the case. In case we have a zero, then the if-1 unit triggers the multiplier to not do any sort of multiplication, and the multiplication is just skipped. If-1 unit is capable of computing entirely number of multiplications in parallel, and it is compatible with both SpMV and SpMM operations. Now these IMU units, they are arranged together to make the diagonally sparse multiplier unit. If the DR matrix predictor predicts the matrix to be diagonal, Piprima triggers the DSMU unit. The DSMU unit, it only deals with the matrices if they are diagonal, which means DSMU does not need register to all the partial sums, and hence we can just get the output and forward to the output buffers. The next one is RSMU unit, which basically deals with the cases in which the matrix is random. The number of non-zero values are already known to the compute unit by the virtue of the NNZ per row predictor. Based on the predictor, RSMU needs that number of non-zero values equal to the prediction and allocate each of them to an IMU. As you can see, these IMUs are the partial outputs of IMU units are pushed to the contiguous probe registers, CVRs, where in the next step, these values are accessed using an adder tree, and they are reduced to give one single output of a given type or a given matrix. Piprima leverages the predictions that enhance the fine-grained load imbalance. The advantage of prediction is that both RSMU and DSMU, they harness the fine-grained parallelism by allowing each IMU to do entirely number of multiplication operations at a time. Piprima informed by the NNZ values per row due to the prediction can now employ multiple IMUs concurrently and does not have to segregate the offsets load and values indices load. The next is the evaluation and results. We use the scientific computing workloads from the SuiteSparse dataset. We also ran experiments in synthetic matrices to allow us to change the density and see how the Piprima is working. We also tested our architecture on transformer workloads, which are relatively denser than SuiteSparse matrices as well as the synthetic matrices. We use Extensor and Tensaurus as our baselines, and we use accelerators accelerator to build both the baselines and also Piprima. For the RTL synthesis, we use Synopsys Design Compiler, and the library that we used was 45 nanometer. The first and the foremost metrics is speed up. It can be seen that by leveraging the prior knowledge of matrix partition structure, Piprima was able to distribute the multiplication operations, and hence we were able to achieve high speedups. As you can see, the speed up is around 4x, 5x over Tensaurus. Also, in case of SpMV, we are achieving the same amount of speed up. One of the main reasons of achieving this performance improvement is that now with the prior knowledge of the partition structure and also the non-zero values per row, it allows us to distribute the multiplication operations among different IMUs. We also ran some experiments on the workload, on the transformer workloads, and it turned out that Piprima was getting good speedups over the baselines. It showed that Piprima is capable with applications applications ranging from scientific computing to large language models. Next, we studied the relationship between the increasing density and the mispredictions. It turned out that by increasing the density of a given matrix, the mispredictions were increasing. It makes sense because increasing the density results in increasing the probability of different non-zero values per row and consequently increased mispredictions. Here we are studying what is the effect of increasing misprediction. We have set up this ratio of memory accesses and operational intensity. A ratio less than 1 signifies more overhead of prediction components, and that is not required, that is not desirable. While a ratio greater than 1 signifies more head in the traditional decompression steps. It turned out that with increasing mispredictions, the memory accesses ratios and the operational intensity ratios were increasing, which makes sense given the fact that if the mispredictions are increasing, we have to trigger the prediction inspectors more often, and then we have to flush the pipeline more often, which results in more data movement. Piprima only takes 5.621 millimeter squares of area, and it only consumes 544.93 milliwatt power. The prediction-related components, they consume the least share of total power, that is 0.15 and 0.554 of total power. Summing it all up, Piprima presents a novel approach to accelerate sparse matrix algebra, drawing inspiration from a simple local branch predictor. It predicts the structural characteristics of matrices and enables fine-grained parallelism in sparse kernels. It gives significant speed up over solar baseline accelerators, and the prediction-related components stand out as the least expensive component. The promising results in post-quantum prediction mechanism makes Piprima an asset for scientific computing, artificial intelligence, and going beyond the optimization of large language models. Thank you.